Thank you, Zach. Thank you for inviting me. Yeah, super excited to be here. Disclaimer. I'm very bad at timing this. This is the first time that I'm giving this talk. My guess is that I have way too much things that I want to tell you about. So I may not get the end, but I don't care if you are asking your questions during the talk. Better fewer things that are going through and deep than a lot of things that are kind of like just brush upon. Okay, so yeah, what do I want to talk about? And let me move this thing here. So I want to tell you about some of the things that we're doing in my lab to try to teach robots to perform mobile manipulation tasks that involve also navigating in the environment. And we're looking into, I have the manipulation real that has a dual kind of like context, making it in the real world, but also learning in real world. It's something that I've been looking more and more lately, and I'm very excited about to use simulation just to enable her to learn in the real world. So these are the things that we have been exploring. And why that? Well, if you look at what robots we have today, most of the robots, the most successful ones are navigating robots, vacuum cleaners, Waymos that we have in Austin a lot, and also the other kind of like autonomous cars that I'm not going to tell you about. Stationary arms, for sure, is the success of robotics in industry, or even this kind of like weird robots that make coffee in airports and are protected there so that you don't touch anything. But is that all that we want from robots? What are the type of robots that we actually have? And my answer is no. And actually, we did it a couple of years ago. We asked people, what do you want robots to do for you? And let me do that kind of like exercise here with you. Let me give you 5 seconds. And if I give you a robot that could do one task for you, what would that task be? And I'm going to give you 5 seconds to think about it. Okay. Don't incept the idea. Okay, 5 seconds, 5 seconds. So let's figure out. So we were asking people, do you want robots to clean for you? It's very tedious. Do you want robots to show snow for you? Something we don't have to do in Texas, but I think here you have to do very often. Cook for you, or cleaning after cooking, which was one of the things that we discovered. People love cooking. People don't love cleaning after cooking. Doing laundry, which is a solved problem nowadays. Do you want a robot that buys shoes for you? Maybe not. Do you want a robot that grabs presents for you? Some people hate it. Some people love to grab presents. So the question was, what do you actually want? So that is what we did. We went and we collected a lot of tasks, and we asked people, what do you want robots to do for you? And here you see the top and the bottom of the tasks. The tasks are coming from something called ATOS, American Time Use Survey, where the Labor of Statistics asks, what did you do yesterday? So we went into ATOS, we collected a lot of tasks, and we asked thousands of people, what do you want robots to do for you? 92% of the top 1,000 tasks are household activities. So we were hand-waving robotics, but now we have data. We actually want Rosie the robot to help me at home. And that is great. But if you think about what Rosie the robot needs to do, what are the capabilities that it needs to do mobile manipulation. And mobile manipulation is really hard because it's long horizon. A lot of tasks are going to be contact rich. They're going to be forceful. And for a mobile manipulator to help you in a home, it needs to be very general because every home is different. And of course, you're not going to be able to solve that with a stationary robot or with a robot that only navigates. You need a robot that is able to do both. Matter if it has legs or not doesn't have legs. I will have been discussing that with some of you today. But you need to navigate and you need to manipulate the world. Mobile manipulation. And mobile manipulation has advanced a lot in the last just few years. So this is coming from physical intelligence. They are bringing a mobile manipulator to a new house. And this mobile manipulator is able to pick up clothes from the floor and kind of like put them in the right basket and some other mobile manipulation tasks impressively with a lot of generalization. This is great, but there is something that worries me, and is the amount of data necessary. So to train and to evaluate this model, they require 400 hours of teleoperation mobile manipulation data to perform tasks similar cleaning and tidying tasks. So this is very impressive. They generalize to an environment, but the cost is very high. 400 hours of teleoperation data is a lot of data for simple tasks. How does this scale up? And the hope is that this is going to be like the LLM moment, the VLA moments, the VLM models were trained for so many tasks that at some point you interpolate between tasks. The problem is to get there, we need a lot of hours of data first in order to train for a lot of tasks so that we can cover a large variability. And this is coming from Kenny Black from physical intelligence. The amount of data that is available for robotics compared to the data that was available for LLMs is several orders of magnitude much smaller. What that means is we're going to still have to wait and collect a lot of data until, if it works, we see that generalization to new tasks without having to collect data for that specific task. So in my lab, we're looking at an alternative path. Can we find new paradigms in which we need less data to train mobile manipulation tasks? And this is what I'm going to be telling you about today. Some of the ideas that we're exploring on how to train for mobile manipulation with not so much data. So the first one is very simple. If you don't have much data, can you squeeze out as much as you can from the little data that you have? And I will tell you about some methods that we have developed to do that. The second idea is, if you don't have so much data, could your robot safely go around and generate more data, explore in a safe manner, ideally in the real world? That is something that I will also tell you about. And if I come to that point, can the robot make better use of experiences from the past in order to not have to collect this huge amount of data? So use memory in order to reduce the dependency on large amounts of deliberated data. Okay, so let me tell you first about how to squeeze the maximum out of the demos that you have, about the data that you have. One idea is to look at how humans learn to perform tasks. And very often we look at another human performing a task, and then we try to imitate it, but possibly we're not able to do it with our own embodiment, so we adapt to what we can do with our own embodiment. Can we do something similar with robots? Can robots look at how to perform a task and adapt it to their own embodiment and their own capabilities? So that is what we did in our first project. The setting is like this. The robot is looking at a human performing a task, and it's going to be trying to perform that task with its own embodiment. This is after adaptation, but the idea is it needs to adapt to its own embodiment to achieve success. And we want this to be done in a safe manner and as autonomous as possible, so that you don't have to intervene, you don't have to reprogram the robot. It does it on its own. This is complex because the first thing is the robot needs to understand for a mobile manipulation task, what are all these sub-steps and what are they achieving? The first sub-step, the human is navigating, there is grasping something, there is bringing it there. What are all these intermediate steps that it needs to achieve success for? And then, as I mentioned, it needs to adapt to its own embodiment. The way in which a human moves is not the way in which a robot needs to move. The morphology is very different. So there's going to be some variations that it needs to have. And all of this safer and autonomously. I don't want to be there with emergency stop my students there the whole time. So how can this be done in an autonomous and safe manner? So this is what we presented at RSS with a method that we call SafeMimic that has 3 elements. The first one is taking one single human video demonstration and extracting all the information out of it, parsing the information in the video. For that, what we did is to use a hand and body tracker developed by George Pavlikos, alumni from here. And with that, we can combine with a VLM and figure out what are the phases of the manipulation task or the mobile manipulation task that my robot needs to achieve success on. We can also use the motion that we have seen the human to perform, the navigation and manipulation actions, and directly translate into the robot. This is not going to work, and I will show you the results later. It's going to fail because you need to adapt to the robot embodiment, but it gives you an initial guess to start exploring in the real world. How does this look like? Here you see a segmentation of the same video that we have seen before, where the human navigates, picks the pot, places it in the sink, and toggles on the faucet to fill the water into the pot.
That's a quick question.
Yes.
What about the scene? You have to reconstruct it as well.
We don't reconstruct the scene.
But then, how can you model the human actions are very dependent on the scene, right? So
yes, we assume that we have a very similar scene for the robot to perform. It's going to perform the task in this environment.
the robot is going to perform in the exact same scene.
is going to perform the exact same scene. Yes. Correct.
I have another question.
Yeah, go ahead.
Do you give any information to the LLM about the granularity of the segmentation?
I will have to
Just-
double check the prompt. It was a VLM, so it was analyzing also the images, and we have some prompt that was Arnav, our great undergrad who took care of the segmentation. It's a combination between the information of motion and the information from the VLM, because both have noise, but together, so if you just figure out how much the human is navigating versus how much it is moving, you get a coarse navigation versus stationary manipulation versus navigation while manipulating. But that doesn't tell you much about the semantics. The VLM is pretty good about the semantics and about what object is being actuated on. So there is a combination in there, but I don't know exactly the prompt.
But so the prompt is biasing the outputs that you're getting of like navigate to the pods, big pods, because the problem with navigate with segmentation is how granular do you want to get?
Yes.
You know, like in terms of like the actions, right?
Yes, we don't give the exact segments or the names, but we basically prompt it in a way of, okay, I'm a robot, I'm going to be performing this task. What are the segments what are the sub goals that I need to know in order to perform this task? So there is kind of like a guidance into the LLM prompt so that you get some useful granularity, not too much, not too little. Yeah. Okay. So this is to kind of like parse the single human video that we are going to use as input. Then we need to adapt it to the robot. And that we want to do it in a safe manner. So how does this look like? This looks like this. Here the robot is going to be trying to imitate the part in which it grasps the pod, and tries to put it in the sink. And what it's going to do, the robot is going to predict few actions and figure out which actions are safe and which ones are not safe. If it doesn't find any action that is safe, it will backtrack and try in a different path. So this is kind of like, you can think of some Monte Carlo in the real world, so to say. And if it doesn't find any path, even going backwards, it goes all the way back and tries a different mode, a different grasping mode, to try to find a solution that achieves success for that specific segment. The success is automatically detected using the VLM description of what is the goal of that phase of the task. So how is this safe or is not safe being predicted? We train very simple safety value functions in simulation that tells the robot, is my current state safe or unsafe? Is the future state safe or unsafe if I take some action? And with this, we can roll out, we can kind of like sample possible actions, query our value function that will tell us, I think you are going to do something unsafe if you do this. How we train this is in simulation. We just have some privileged information about how much force is being applying, and if it's too much force, this is unsafe, or if the object of interest is being dropped, that is also unsafe. So we can generate a lot of data, and that is what we do in simulation, on things that are safe and unsafe, so that we can pre-train these models, very simple models, in simulation. These models are going to use point clouds as input because point clouds transfer quite well from simulation to real world. And this is already enough for us to go into the real world. The models are a little bit too safe. So sometimes they're kind of like, oh, don't do that. It's very unsafe, but it's okay because we prefer to be too safe than too unsafe. And with this, we can adapt safely in the real world. We use the simulation only to learn these safety priors that we can use to directly in the real world adapt.
Can I ask
Yes.
Okay, you mentioned that the models are sometimes too conservative, right?
Yes.
But are you doing anything to kind of enforce them? Because in practice, the error could be either that they're too conservative or they're too permissive. And obviously, for the safety filter, you don't want it to be erring in that way.
Yeah.
So how do you ensure that you are in fact on the conservative side?
We don't ensure. That is our empirical evaluation. It has more false negatives, false positives than false negatives, but we cannot ensure that.
I see. Is it, I mean, you could potentially, for example, choose to be conservative, right? Like you could choose to say that I'm going to, in my Q function, for example, if I learn distribution or something, I'm going to err towards the higher side of the Q function. And there are techniques to do this kind of like safe Q learning style stuff, right?
Yeah. Yeah.
But you just found that it happened to, in this case, conveniently end up.
It happened to us, and I'm also a bit hand wavy because to evaluate this is not easy. How do
Right.
you evaluate the counterfactual of what would happen if you actually do that? Our evaluation is purely in simulation, but in real world, we assume that it's similar, but we don't know. We know that my value function says now it would be unsafe to do that. You're gonna apply too much force, but I don't want to break my robot in the real world. So yeah, there are some of the value functions that we couldn't evaluate in the real world.
Gotcha. Yeah, thank you.
Just we know what kind of force it would safety flag.
What is the force input in
Any
the?
kind of force or
We simulate a force torque sensor on the grist. That is also what we have, and is what we simulate also in the simulator. So if it's feeling too high forces on the force torque sensor grist, then we assume that this is unsafe. We could have gone full kind of like observability and just computed contact forces directly because we are in simulation, but we were using the same simulated real sensor that we have in the real robot. Yeah. Does it answer your question? I'm not sure if I understood. Okay. Yeah.
So first, you mentioned you actually backtrack and select different modes.
Yes.
So where do the modes come from?
The grasping modes come from a generative model for grasping at the beginning of each of the grasping parts.
So
Or if it's not a grasping part, if it backtracks to a different path, it just queries a different path from the navigation function.
is that from the human video, or is
The human video skews so that we test first. So what we have is a generative model that tells us these are the possible grasps on the object, and we skew the first mode that we test to be the one that is the closest to what we have perceived the human to grasp.
Oh, and okay. Second, where did the wind come from in real?
Oh yeah, there is a let me go back. This is not back, it is forward. There is an RGB sensor in the head of the robot.
On the hand.
Yeah.
I see. Okay.
No question.
Yeah.
Sorry.
No.
It seems that you define a safety Q function, so it seems that, correct me if I'm wrong, so you want to say define this kind of safety reward, and then you have the current safety plus the future safety rewards in this formulation. And I think you try to make an analogy to rewards, but for rewards, it's like, even though the current action may not give me high reward, but in the future, if follow this trajectory,
Yeah.
I can get high rewards, I can still take this action.
Yeah.
But if you think about safety, let's say if this action is not safe, even though the future states might be safe, but I cannot take this action. So in this
Yeah.
case, do you think is this formulation?
There is an equivalence between our safety value function, and this comes full kind of like disclosure. This is some ideas that Chelsea developed a couple of years ago. You can fully map into RL. We are not fully mapping into RL because we don't have reward for the task. You can think of it if you can consider each of the phases of the task to have a kind of like a termination reward, then maybe you can kind of like think of it as a reward, as a full array problem, but we're not doing that. Why we call this a safety value function is because in a 2-step ahead horizon, it's going to tell you if it's going to be safe or not safe, but it doesn't go all the way. It just tells you a few
The
steps.
horizon is different.
Yes. So it's not a multi-arm bandit problem because it has some horizon, but it's very, very short. Okay.
Roberto.
Yeah.
What were the?
I'm not going to reach the end here.
It might be.
Very cool and interesting, and I'm just curious. So, what were the policies that were used for exploring to learn the Q function?
Random actions in simulation.
Oh, okay. Random.
There is
actions.
no policy.
Okay, I see. So it might end up being conservative even just for that reason, that you're performing random actions. You're effectively learning. Are you learning the optimal Q star, or are you learning the Q for the exploration? Is it a
We're learning the Q for exploration. There is some mismatch
Okay.
distribution
I
between,
see.
you have a guidance from the human that is the
Yeah.
one that you're going to be using in real world.
I see.
The exploration that we do in simulation, we want to be as general as possible with these functions. So we don't do it per specific task. We go in simulation, we grasp an object, we move around,
Okay.
and we feel if the object is dropping, if we're colliding with things. So that is the type of pre-training we are doing. We want to be as general as possible so that we can apply to all the tasks that we are doing at the end. So yes, there is a mismatch between the action distribution that you are going to see when you are exploring around the demonstration versus the action distribution that generated the safety Q functions. That's
So I'm imagining, for example, if you have to perform a task that involves a knife or something, right? Like you're going to be just like right out of the gate, it's impossible to be safe. because if you do random actions, you can hurt yourself in one of 10,000 different ways.
Yeah.
Right. You see what I'm saying? Like, it feels like somehow it has to
Yes.
be tied to the fact that you have a particular policy. That's the thing that you want to measure safety for, right?
I think the overall assumption is there is a universal set of unsafe things to do, which is also not true. It's not exactly what you are going with the knife idea, but it's something we discussed for this project, which is should we activate and deactivate different unsafe value functions depending on what task or what phase of the task you are in? Because in some cases you don't want to, for example, collide with your hand, but in some other cases, colliding is what you need to do in order to manipulate the work.
Yeah.
So we didn't do it because our value functions are kind of like for the extreme. I can collide with my value function, it's gonna say safe. If I'm applying 100 or I predict I'm gonna apply 100 neutrons or 200, then is when it's unsafe.
Nice.
So we find kind of like a minimum common denominator that works well. But where you're going is these safe or unsafe are task specific. And sometimes things that may be unsafe are not unsafe or going to depend on the context of the task.
Yeah,
And that is completely true.
Policy specific too, right? Like it has to be based on the capabilities of the robot and its current
Yes,
policy.
the capabilities of the robot are on the simulator, at least the
Yeah.
physiology, but yeah, the capabilities of the policy and how good it is, it's going to depend on how.
Let's continue the conversation offline.
Yeah, okay. All right, yes, okay, policy memory. So all of this, so the adaptation happens from one demonstration, and that is great. But what happens if the robot has to perform the same task again? Does it need to adapt again and learn what are the actions that actually are safe and work for its own embodiment? Well, that is wasting a lot of effort. So what we thought is, can we actually memorize what worked for the robot so that it doesn't need to readapt if it performs this mobile manipulation task again? And for that, we do something very simple. We kind of like map the strategy, the adapted strategy into the environment, again, into the point cloud. For example, what grasps work, what trajectories work to manipulate an object. We create geometric augmentations and we train a point cloud-based policy that, given a new point cloud and a task description, is going to tell us what are the initial adaptations that work the best before. So instead of starting from the human motion, once that we have learned to adapt, we start from our adaptation. And that allows the robot to already know what type of grasp should it be using or what type of strategy to manipulate an object like a drawer worked before, even if it navigates in a different way, because now the strategies are mapped into the environment. Okay, so how does this look like? We tested in 7 tasks that are mobile manipulation tasks, navigation, manipulation, some contact reach tasks, opening drawers, opening ovens, putting things inside. And I want to remind you that this is the only video that our robot gets as input to perform these mobile manipulation tasks. It's the single demonstration, just one video. And here you see the robot adapting. So you see the filling the pot that I showed you at the beginning as an example, but there are all the other tasks about loading the oven, putting the object in there. It's not going to be very successful with that grasp. It will have to change the mode. So it takes a while. It's a lot of trial and error, going there, figuring out I'm not going to be able to do it. Let me go back, let me change the grasp. But it achieves success in all of these tasks that are quite complex, multi-step mobile manipulation tasks in the real world. And again, single human demo, not hundreds of them.
Single human demo.
One video.
Yeah, one video, but it was on the same environment that
Yes.
the robot has seen before.
It's the same environment, yes.
Same environment, and the robot has never seen this task before.
No.
But
That
the
is
same-
the generalization we get. Of course, we don't get the PI generalization, new house.
The same object.
Same objects in the same environment. Yes. So this is more like I have a robot and I want to tell my robot, I want you to do this task in my house every day.
Yeah.
I'm going to teach you my
You
task.
show a human demonstration.
And you show one single human demonstration.
And can you also tell us how much does the retargeting fail? Like how much does the computer vision fail?
I think George will be the one to ask that question. The retargeting actually fails, and I'm going to show you the bars. So directly retargeting is flatline because it's very different. So even if it's not a failure of the computer vision, maybe it's a failure of the computer vision. I don't think so. It's a failure of, it's just not the same embodiment. So what people are working on a lot now is how to transfer from human motion into robot motion with some non-direct transformation. Here you use a direct transformation. It's just too different. It's just the hand of the human and the hand of the robot is two different morphology. It's not possible to transfer it with a single function. So yeah, that is where I think the failures come from. There was some question there? Yeah.
Yeah, I was just, so I didn't get all of it. So, getting your signal motivations just uses some chunk of the data.
Yeah.
It's not sometimes you're using simulator, you're still generating.
Yeah.
So it's not a more, I think it's less of a question of like sample efficiency, but more where can I get cheap data to train and then transfer to the real world?
Yes.
It's great, right?
That is a better way of putting the questions. Yes, it's not less data. The prior has to come from somewhere. So it's still data driven, just coming from simulation, which is much cheaper than collecting hundreds of demonstrations. But yes, there is a lot of data involved. Yes.
First question would be reducing data. I think there's some.
Yeah, I think I have another two projects that looking at the clock just for squeezing data that go more into that direction. I think there are a lot of things that we can do to be a little bit more efficient with the data that we have. For example, multiply the data in an autonomous way, which is the second thing that I want to tell you about. And the third thing is, given data that you have some data, how can you pick the best data for specific training process? It's not getting more out of the data, it's being more strategic of what data you use. Yes. Okay. Okay, quantitative results. What we have here, green bars are our method, SafeMimic, adapting, and what is the success rate. And here, if the adaptation is dangerous, so if we stop the adaptation, that is a failure. So we're not just letting it try many times to adapt, it's just kind of like one shot. If we do direct execution without or with safety value functions, these are the first two bars. In most of the cases, it's flat line. So that is where I was saying it doesn't achieve success. In boxing an item, it achieves success even without the safety value function. So the safety value function doesn't trigger anything, and it achieves 20% success, which is okay. We also tested again exploration without the safety value function, and we are the ones that kind of like are there to place the trigger, or we have some other kind of like forced or sensor automatic watchdogs that if it's pressing with too much force, we stop the execution. That is also almost always a failure, except in these two cases. And then we also tested imitation learning because we're generating a lot of data. What happens if you train a policy with all the data generated in simulation plus the one demonstration in the real world? Does it? And can you do anything? It was interesting that in the boxing and a box, you actually achieve some success. So imitation learning can work as off the shelf with the amount of data that we have, but for the other task, it doesn't perform so well. Okay, and for the memory, what do you get out of the memory? What we get is that if we use this policy memory that maps the adaptation that was successful to the environment, we get that 58% reduction on the samples that we need to run when we perform the task a second time, even with a different navigation pattern, which is a lot. The hope is if you do it many times, you're going to get something a bit better so that you don't need to adapt. Cool. So this is something that we presented at RSS this year. Arpit was the kind of like main person behind that. Okay, so that is one way in which you can squeeze out of your data, or conceptually, you're generating cheaper data that compensates for little data in the real world. Let me tell you about a second way in which you can squeeze the maximum out of your demo. So the idea is simple. What happens if you would collect a demo? And this is Telemoma, one of the systems that we did for teleoperation. And you could multiply that demo magically and generate a lot of variation. That is really helpful, especially for mobile manipulation, because every time that you navigate, you're going to have a different perspective. You're going to have a slightly different setting. You want to have a lot of data that allows for that variation to be covered in your policy. So that is what we did for mobile manipulation. And this comes from, where's this mouse coming from? That's curious. Yes, so this comes from this family of techniques that that generate data from one single demonstration. So what we do is we teleoperate a robot in simulation, we collect a demo, and then we pose the problem of generating more demos as a constraint optimization problem. We want to maintain reachability on the objects, we want to maintain the objects in the visible space, and be able to generalize to different configuration of the same objects. And if we do this in simulation, we can actually do it very easily and augment from one single demonstration into multiple demonstrations, thousands of demonstrations that allows us to have different navigation behaviors and different manipulation behaviors using one arm or the other for the same task that we have demonstrated once. So we're trying to kind of like multiply this single demonstration with some ideas from constraint optimization. So how this looks like, we get a single source demonstration. We annotate a little bit more of information of what arm is used, what object is being performed that can come from a VLM or manually. And then we extract the most important part, which is the contact reach part, because that is the most difficult one. That I leave it for Michael. I don't know how to do it. So that part we reproduce as it is. But the other parts, if I navigate differently, can I filter out what poses of my robot are available to perform the manipulation task? What poses of the robot see the object and see the object during the entire manipulation task? So we filter out what valid base poses we have, and we generate trajectories that go to that pose, reproduce, move the arm to the initial position, reproduce the contact part, and then retract. And all of this is done in simulation, super easy. And we can get one demonstration, multiply by many demonstrations with different initial navigation and post-navigation strategies. So that is what we did for a few tasks, like pick up, tidying the table, putting dishes away, or cleaning a frying pan that requires to use both arms. And here you see some of the generated demonstrations in simulation. This is generating from a single demonstration, different ways of performing these very simple tasks. All of these automatically generated. Of course, you have full observability in the simulator, so you can make use of all of this. The only constraint part comes when you have to be at the location that the object is reachable from, and the object should be in the field of view so that you can generate these images. Oops, that doesn't work. These images that are what we are going to be using to train visomotor policies. Okay, so what we get from this is training policies that are very robust to any navigation strategy, which is very helpful for mobile manipulation, because in stationary manipulation, you are not going to change your base or your camera, but in mobile manipulation, every time that you navigate, you're going to slightly have a different navigation, and you need to be robust to that. Yeah.
So this is cool, and I'm wondering. I mean, this is an actually really interesting point about the difference between mobile and static manipulation.
Yes.
That the coordinate frame is constantly shifting, and so it creates a weird kind of data scarcity.
Yes.
But it also feels like the kind of structure that we can exploit in ways other than just data augmentation, right? Maybe like partly the problem here is that we're producing our action spaces in the frame of the robot. Like it feels like there should be other solutions to this that kind of take advantage of the fact that there is another coordinate system in the world we could be doing things in.
Changing the action space is a good idea. I would, if I think thoroughly about it, I think the intrinsic problem is that we are using directly images as input.
Yeah.
And I think that is not a good idea in mobile manipulation.
Right, right.
Because just one tiny degree is going to change all your pixels.
Yeah. Exactly.
So how do you generate this invariability to a new camera pose?
Yeah,
You can do brute force and generate data on different camera poses, or think a little bit about what is the representation of your input. I think there is space to do something there, but it's true that visomotor policies, just using RGB as input, have been so far, and I don't think the depth input policies are there yet at the level of RGB policies. But yeah, I completely agree, and I think action space, but also observation representation is something that is, we need some other representation for this.
Yeah, thank
you.
Yeah.
Do you find that with enough data augmentation that you put a policy that actually generates the ambiguity and how you approach the object? Or is it more like given a base pose, there's going to be one specific reaching motion that's something?
There is no ambiguity, at least not in the amount of data that we get. But it's true that if if you actually generate a lot of data, you can start to get multimodality very easily. And I wonder if there is an interesting inverse problem that learns what should be the right mode or what should be the right base pose. We haven't gone into that. We're just being reactive in a sense of whatever base pose I want to be able to manipulate. But can you be more clever and figure out what base pose is the best one given all the data that have generated? But no, we haven't seen that multimodality in the data that we generate. Okay, cool. This was in simulation, and you may think, okay, simulation is nice, but what about the real world? So we tested with the real world, and the real world, the recipe is we can generate thousands of demonstrations in simulation and then fine-tune, with some data in the real world, just 50 collected demos in the real world and fine-tune with that data. And we see that if you use the simulated data as pre-training, it really changes the game. For example, if you try by zero, just fine-tuning it with the 50 demonstrations, it achieves 0% success on a simple task like grasping a cup. And I was discussing with someone before, yeah, by zero is surprisingly very good sometimes and very bad sometimes. So this is one of the times that is really bad. But if you pre-train with our simulated data, you achieve 60% success. So you collect a few demonstration simulations, you multiply by thousands, you pre-train with that, use the same amount of real-world data, you increase the performance by a lot. So it's a nice trick. You can even do some kind of like cross-embodiment, collect the data with one robot and transfer to another robot. This is all kind of like kinematics and kind of like Cartesian poses. So that is not that surprising, but it's actually nice because you can transfer from different morphologies. So yeah, this is a paper that is with my collaborators at Stanford. So if you want to check it out, it's here. And what we're gonna be doing in my lab next is, I'm still not super satisfied with the real world results of fine-tuning. So actually, can we do this in real world? Can we actually collect demonstrations in real world, a handful of demonstrations, and multiply them? So that is what we are looking at. So imagine that the robot has to grasp an object in that shelf. One option to make your mobile manipulation policy robust is to take demonstrations from any base location, and then you're going to be robust to where you are navigating. That's going to be very intensive. So what happens if we can just collect a handful of them, one or two, and then extend to the other locations in a kind of like generative way? So this is work in progress, but they're going to show you where we are right now. The key idea is we're going to be using a segmented Gaussian splat to generate from the few demonstrations a model that we can then use to generate virtual views for mobile manipulation to perform the same task, using some other tricks on how to kind of like generate the robot, inverse kinematics, and some soft constraints. We can generate data from any new perspective, changing even the objects that move between demonstrations. And all of this is real world data. So we want to do everything in real world. But again, coming from a handful of demonstrations, multiplying into hundreds, thousands of virtual demonstrations that contain the same manipulation information, but just from different perspectives. Very important in mobile manipulation. Okay.
So Roberto.
Yeah.
The virtual demonstration is the same action, but it's just like it's just different viewpoints, right? So you're not changing the actions.
We are not
Okay,
changing
so
the
you
actions.
still have that handful of actions, but like imagined in from different viewpoints.
Well, depends on how you consider the action, how you are defining it. You're changing your reference frame. So if your robot is changing, officially your actions are changing, because I mean, I was moving to the left now I'm looking like this, I'm moving, like, yes, they are changing, but no, they are not changing. We're just changing the reference frame.
Depends on which reference frame, like if you're in the reference frame of the object.
Then it's the same, exactly. In the reference frame of the object is the same. So it's kind of like that. We are mapping into the environment. We are just changing the robot perspective, but the actions remain the same. There is a little bit of adaptation because now your base is going to be different. So we may need to kind of like move in a different way to reach there and move. That's going to be kind of like inverse kinematics and some softness in the trajectory. Some coherence, but yeah, basically the actions are the same. Okay. Questions? No? All right. So this was second way, and I hope this was a bit more like, okay, you are squeezing more out of your data. Third way, and I don't think I'm going to have time to go into exploration or memory, but that doesn't matter. a third way in which we can squeeze the maximum out of the data that you have. Okay, so here the idea is, imagine that you have already a data set, and we're already start to have some data sets. We have OXC, we have Droid. They are very large data sets, actually quite difficult to operate with at the scale of academics and what we can train. What would happen if we can actually pick the best parts of our data set to train the most performant model? So it's again not generating more data, it's just being strategic of what data you use to train. That would be amazing, but it's kind of like a chicken and egg problem. How do you know what data to use? So in other ways, in a visualization, imagine that you have a very large data set, and these are all images from OXC, and you want to perform just a specific task. That is your target. And you want to pick up the data that is the best to train your model for that specific task. That's going to be a lot of data here and there. And what the strategy that most baselines or most kind of like existing works for data collection or data curation are doing is using some form of similarity. The most similarly looking trajectories or the most similarly moving trajectories are the ones that are going to be the most healthy. But our hypothesis is that this is sometimes going to fail. You want to kind of like approximate this kind of like blob in the similarity space. Some things that are not that similar may help you to train your model in the best way. So how do we actually figure out what data is that? So yeah, in a bit more formal way, what we want is we have an initial data set D, and we have a learning algorithm A that is going to provide us a policy, in our case, an imitation learning policy, and we are going to evaluate what is the performance of that trained model, of that policy pi with some performance metric M, that in our case, usually in robotics is success rate, for example. How successful is my policy? So then the problem is this optimization problem. How do I find the subset of data that maximizes my performance metric given the training process with that subset of the data? So solving this is hard because basically if you try to do it brute force, you're going to have to use all subsets of the data and figure out which one is the best one. So that is going to be very complicated. So what we used to do this is framework that is called data models. And data models are models that at high level approximate what is the metric given a subset of the data. So it characterizes subsets of the data in order to figure out, given a subset of the data, can I predict how good my training process is going to be? With this, we can go and figure out what parts of my data are the best ones to train my model, and then try to get the best performing model. So I'm not going to go into the details of how data models work. I'm just going to tell you we tried two different variants. One is regressing, given a subset of the data, what is the expected performance. The other is using meta gradients that is called, which is basically to do some steps of gradient descent and figure out what subsets of the data are going to be better based on the magnitude of those gradients. But the key idea is that we still need to compute several times this metric with different subsets of the data, but the amount of tests that we need to do is much, much, much smaller than if we would test all subsets of the data. So that is what we integrated in a new method that we call data mill, which is data models for imitation learning. And here we have to solve a couple of extra problems. The first one is the metric. So I told you that usually we use success rate in rollouts. If we do that, we're going to have to train models with subsets of the data, roll it out, figure out how successful they are, and that's super costly. So instead of that, what we use is a proxy objective that instead of evaluating the success of rollouts in the real world, evaluate how good are we at predicting the actions in a held out set of the data. You can think of it as a validation set. And that actually performs pretty well. We compare, this is doing data models with full rollouts in simulation. And this is using some of the variants that we use with our validation set. And we can approximate pretty well what is the selection of data that a data model with the ground truth evaluation would have, just with a validation set that is much cheaper. We don't need to roll out anything. We just evaluate the prediction of the actions in that validation set.
Is it that you have data that's actively harmful, or just that maybe you have competing strategies to be trained on both of them, your policies?
That is a good question. I don't know. I mean, we did some introspection in what type of data. Usually it gets into closed data, but sometimes there are surprising amounts of data that it ranks very low, which could be the reason that you're saying. It's different ways of doing the same task, and maybe it's just selecting one mode, and it's better to train for that mode than try to train with all the modes and fail. There is so much data that is selected because at the end it's a subset, but it's still a lot that is difficult to introspect. But we have a lot of different variants of trying to figure out, is it kind of like selecting the data that we expect or not, especially semantically. It actually takes a lot of the long tail of data. So data from tasks that are very unrelated, but our method finds them useful to train the model, which was surprising.
And did you perform the experiment where you removed that kind of more surprising data and then retrained your policy and observed that it was?
Yes, that is basic.
Performance?
Yes, that is usually most of the metric of the baselines. We use a lot of baselines that use, for example, semantic similarity. How close is your subset of data, the definition in language of this task with the task that you want to perform? That is one thing that we kind of like observe, and that is the long tail. You have a task that has a completely different language description that our method finds useful. A method that uses semantic similarity would not use that data. Image similarity, we use all these baselines from similarity metrics.
The other kind of thing that people have done for data like that, I mean, the problem setup as you described it almost sounded like an offline RL, like learning from play kind of problem, right? Learning from play is kind of.
It's data curation. So there is a kind of like another method from Janet that is doing something very similar. It's called Cupid. In their case, they need to roll out and they do full back propagation. So you can do it in an RL step. And that was our idea for the second step. Can you kind of like roll it out, so to say, and kind of like figure out what would be the best strategy to get full success at the end of the task. So that involves a little bit more of temporal and kind of like coherence. But we didn't go into that. We just used the validation loss. If you're interested on looking more into the offline RL connection, check Cupid. It's not offline RL, it's actually online RL. It also rollouts in the real world, but it kind of like, yeah, their loss is closer to a Bellman loss, so to say, instead of a validation. Okay. Yes, okay. So the things that we adapted, no rollouts. We don't want to do rollouts. It's very time consuming. We only use the validation loss. The second is, what is the form of our subsets of data? Instead of treating each data point, image, action as individual, we take small segments and we use the temporal coherence that reduces the problem and makes it more tractable. And then the third thing is about the training process itself. We did a training recipe in which we mix our validation, kind of like what is the task that we are training for, with the data that we are selecting from the large data set. So some form of co-training. Okay, so some experiments, what we did was to train for multiple tasks, extracting all the information from OXE, from the OXE data set, and we tried on different single task policies. So basically our target task is a single task or multitask policies. So our validation loss contains different tasks, and we train one single policy that is good on doing all these tasks. And we achieved very, very good success on this using all the data from selected from OXE. One very cool experiment that to me is the most interesting one. We train for Iago robot using OXE data. OXE doesn't contain any data for this robot. So we collect a few demonstrations with our Iago robot that we use as validation loss, and then we select the most useful data from OXE to train a policy that achieves success for a new robot. So that was really, really amazing. Here you see the comparison. You have a set of baselines that are taking different ways of similarity, and that is the way that they do curation. And we compare them against DataMan, which is our method that achieves very high success in all the cases. Okay, cool. Yeah, so if you're interested, you can take a look. DataMill, this is a collaboration with some folks from MIT, which are the ones that develop all the theory behind data models. And yeah, we decided to apply it to robotics And that was a lot of fun. Okay, so that was the first part, and I don't think I'm gonna get into the second and third part. I told you about SafeMimic, one single human demonstration, video demonstration, and the robot is able to adapt it and perform it. Mimic Gen, one single human demonstration, one single demonstration, and we multiply it to be more general for mobile manipulation. And data mill that takes a different approach, which is, can I actually select from the data that they have the most useful one instead of trying all the data that is there? And I'm gonna cut in there.
If you ran data mill on Mimic Gen, how much of that data would it cut out?
That is interesting, kind of like a loop. Okay.
Multiplication harmful.
Okay, I'm gonna tell you now that we're here among friends. One thing that we're doing is turning around data mill and saying, can we use data mill to guide data generation? So I think you're going into the same kind of like next thought. How data mill can tell us what data to generate, what demonstrations to generate to improve the performance of our model. And we're exploring different avenues, but kind of like the idea that you have, how can you collect this data selection to data generation some way so that you generate the most useful data? Yes, cool idea. Yeah.
Is this online generation, this selection of the data, is it completely primarily for the fact that every training is on a graded descent, or could you imagine other paradigms?
It is very general. So at the end, that's why I try to give you the general view of how it works. You just need some metric that tells you how well your learning algorithm is working on subset of the data. That is as much as the general data models need. Now, our application to robotics has some specifics of how to do it more efficiently for robotics and for imitation learning in robotics. If you want to do something like more closer to RL, you would not do, for example, this validation loss. You don't have a validation loss in RL. You would do a different thing. For example, in that case, this loss that we use, this is our loss. It would be a different loss here if you would not use behavioral cloning. You can use, for example, a kind of like an objective, more RL objective, more closer to Bellman, backups, TD, and then you plug in at your metric something different. So yeah.
So I have a question on data mill.
Yeah.
So goes to some extent against my intuition, and I think Michael had a very similar remark. Technically, the more data you have, the better it is.
Yes.
If you are not getting better performance with more data, it means that your model is not capable enough. So you have to scale compute. At least that's what we see in the scaling laws for LLMs. And why is this not happening here? Or where is it that we're being lied?
So the first lie is about LLMs because the first test bed for data models were LLMs and computer vision algorithms. How do you select the best images to train a model that does some, for example, object detection in a better way? And here I think it's more about constraining to what matters to you. So maybe you want a generalist model. If you want a model that detects any object, you need as much data as possible. Or if you want a multi-task policy that does everything, you need all the data of the world. I'm not sure. But in our case, we're kind of like specializing. If you want to an object detector that detects between dogs and cats, probably pictures of the sun are not very helpful, but pictures of dogs and cats are going to be the most important ones. So that is my intuition. It's more like kind of like if you are focusing.
It's a that is I have a specific task, and maybe I don't have a lot of compute, so I cannot have a very big model.
Yeah.
I just want to focus on whatever is important for this task.
Yeah.
But I don't care about generalization.
Yeah. But it's true that theoretically, I mean, if you have an infinite capacity, a model that trains on one task with the data that you're selecting or on that task plus a lot of other tasks, it should not lose performance on that task. Theoretically, that's true, but I think you reach the limitations of the real world where if you have a lot of other things and a lot of data, you're going to be trading off generalization for performance on a specific task. And that is what we see with VLAs, for example. They are okay, in everything, not very good on anything, so to say. So I think that is to me the trade-off. At some point, maybe we have enough capacity to do it. That is one intuition, yeah.
I think that's really the issue.
Sorry?
Good, take data robotics, for example, we do the reward. Like similar here is like data model.
Yeah.
You can achieve like very good. And also the data scale, I think, we don't know, maybe we just didn't reach that amount of huge data. Like as you mentioned earlier, still very early stage, with really limited like data, even in this. Like there's only 1 year for development, so maybe years later we can have some scale, but for now, maybe not.
Yeah, that could be a hypothesis.
Roberto, have you made peace with the fact that that's about how much material you'll cover? Because I have questions about early part of the talk.
I mean, yeah, it's 4 p.m.
All right. So I wanted to make sure that you weren't hoping to still go on. I still find that early part of the talk very interesting, the SafeMimic part.
Yeah.
And I am wondering, so there are two things about that thing that I really like. One is the idea that, I think you touched on this as well, that somehow a lot of safety seems like it's kind of common sense, you know, and maybe, you know, my colleagues who work on safety should not take that as a take it as an uninformed opinion, right? Take it as an uninformed opinion, right? It feels like there's a lot of it that's common sense. Like you don't want to exercise very high forces in the world unless the task really demands it, kind of stuff, right? And so that aspect I really like. And the other thing that is interesting about it is using to learn these Q functions in simulation.
Yeah.
And very little like sim to real RL has focused on learning anything other than policies in simulation, right? Or like transferring anything other than policies.
So this is your fault. I was stopping here, but because you are talking about this, the other thing that I wanted to talk about is how can you learn action spaces in simulation that allows you to do mobile manipulation RL in less than 1 hour. So what we learned very, very, very quickly in 1 minute, we learned an action space with unsupervised skill discovery, which basically in a nutshell is learning this skill policy that is conditioned on a variable. And what we're going to be doing in regular unsupervised skill discovery, what you encourage, the reward is that different Cs, the behavior is different. So you get kind of like this was applied to navigation. So what you get is kind of like behaviors that can kind of like navigate in different ways. We use that, but we also use that these behaviors have to also be safe. So what we do is with that, we can go into the real world and learn downstream tasks, like for example, these ones here. And this is moving the base and the arm combined because our action space, our latent action space maps into combinations of base and arm that are safe. And we are able to learn with RL in the real world in less than 1 hour, all of these strategies using input vision.
Yeah.
So this is a second way. I'm exploring different ways, and I was discussing that today, how to use simulation in other ways. So this is one way we're exploring to use simulation. Can you pre-train an action space in simulation that is safe and more efficient to combine your base and arm and go into the real world with this new action space and train with the new action space? So the pre-training is for a new action space in simulation. The real training happens in real world with your new action space.
Yeah, that makes sense to me. Yeah. I think in the Diane paper as well, they were doing things, but there were a couple of follow-ups of stuff like Diane that were kind of learning from offline data or something like this, these vectors.
Yeah.
But kind of where I was going with that original comment was, I'm wondering, for example, is the safety Q function or in general, is Q learning in simulation somehow more robust to sim to real gaps? Is it like, did you find that you needed to pull the same kinds of tricks that people typically do when running PPO to train a sim to real RL system?
To me, it's a lower bar because you're not learning a policy. When I have tried sim to real with a policy, it's a very high bar. Either your policy is well trained or not. Here, we're not learning the policy. We are learning just a prior over what is safe and unsafe. The learning happens in the real world. The same happens here. We don't learn the policy in simulation. We learn the prior that allows us to go into the real world and learn in the real world in an efficient manner. That is how I kind of like more conceptually think about it. The bar is lower on what you are learning from the simulation and what you need to transfer. And even if it doesn't transfer completely well, you still have a learning process in the real world that can compensate for that.
True, but you're never updating your Q function in the middle
No,
of it, right?
we are never updating our Q
So
function.
you could be in a position where your Q function is basically prohibiting you from exploring. the
Yes.
real world, right?
Yeah.
But in practice, you're finding that it's quite forgiving.
For this task is quite forgiving, and maybe we are missing strategies that are good and that we're not performing. And there are some errors still where the policy, our Q function says this is safe, and still our watchdog or my student had to press emergency because it was not completely safe. So it's not one-to-one. So
Yeah.
there is some room there to improve, even to fine-tune the Q functions in the real world. But for us, it was quite good for the task that we were doing.
Very nice. Yeah.
Great. And logistically, I think we are a few minutes over, so anyone who does need to leave, please feel free to leave. Maybe one more question.
Mhm.
So we don't-
I'm here.
So earlier you mentioned like, Kelly, you said that we could sort of achieve like generalization. Also, potentially could like sacrifice the specialists for certain tasks.
That is one intuition I have. I don't know if that's true, but it could be. Yeah.
I guess question is like Kelly and the both or it did not enough people.
Scaling your data set, so creating more data. I think it goes together with the model, depending on the capacity of your model. So if you would have infinite capacity on a very, very perfect model, then yeah, more data is never going to hurt you. But I think there is kind of like a trade-off between how much capacity your model has and what data is it training on. So in some way, if you have a lot of bad data, it's gonna somewhat interfere with learning from the good data. So if you have some way of just using the good data with a model that has some bounded capacity, you're gonna get higher performance. So that is my intuition, but it's true that if we keep kind of like improving our models on their capacity, we may not need to select the data. We can use everything.
Awesome. Let's thank you, speaker, one more time. That was awesome.